Okay. So today we'll discuss about the bridge circuits. So you have AC bridges and DC bridges. A bridge circuit consists of network or four resistor arms, forming a closed circuit with a DC source of current applied to two opposite junctions and current detector connected to the other two arms. So that means bridge circuit is nothing but it is consist of four arms of resistors. Okay, four arms will be there, and from the four arms, two arms will be connected to the DC source, and between the two arms one current source will be there. That current detector, will use the current detector as a galvanometer. So galvanometer will detect the reading of the current. So that is the bridge circuit. So these bridge circuits are mainly used to find out the resistance or inductance and capacitance. So it can be used to find out the resistance, inductance, and capacitance. So, uh, so bridge circuit compares the value of unknown components with accurate known components. So it will compare the unknown components with it. That means in the bridge circuit, suppose four arms are there. No, so in the four arms, the three arms values. So values of three arms will be you can know. So in the three arms, one can be variable. So variable resistor or a rheostat. So we can vary that resistance by we can make that bridge circuit as a balanced or null position, so that we can find out the unknown component. So its measurement accuracy can be very high. So measurement accuracy is directly related to accuracy of bridge components, not of null detector used. Okay, so it will be the accuracy is depends on the whatever the bridge components we are using. So the accuracy is depend on that. One second. Am I visible? Am I audible?
Yes, sir.
Yes, sir.
Okay. There is some problem with camera. Okay. No problem, no? I'm activating camera, but due to some technical issue, the camera is disabling.
No problem, sir. You can continue.
No problem. Okay. So types of bridge circuits, you have DC bridges. In this DC bridges, you have two types. One is a DC bridge, and next one is AC bridge. So in the DC bridge, you have Wheatstone Bridge, Kelvin Bridge, Wheatstone Bridge, and Kelvin Bridge. And in AC bridge, you have Maxwell Bridge. So today I will explain you about the Wheatstone Bridge. So Wheatstone Bridge is an electrical bridge that is used to measure the resistance. So this is mainly used to measure the unknown resistance. So we already discussed in the previous lectures that hardware anemometer. So there, whatever the change in the resistance is, we are calculating by using the Wheatstone Bridge. No, so same thing. So Wheatstone Bridge is more accurate method of measuring the resistance. So it is a more accurate method. So this bridge consists of a galvanometer, two parallel branches, and four resistors. So one galvanometer, two parallel branches, and four resistors. One parallel branch contains one known resistance and one unknown. So if you see one parallel branch resistance, so in that one known resistance will be there and one is unknown resistance. That unknown resistance you need to find out to make that bridge to be balanced or null position. And other parallel branch resistance are known resistances. So other parallel branch resistance are known resistances. To operate a bridge, so in order to operate the bridge, we need to connect a voltage source between the two terminals of the bridge. Okay, we need to connect a voltage source. Okay. So see here, this is a Wheatstone bridge. So you have a galvanometer and two parallel leads, parallel terminals. So with this parallel terminals, um, so one is so these R1, R2, and this is a standard arm R3. These three are known resistances. So as I told you, this is a variable resistance. We can vary this resistance, and this is the unknown resistance. So two terminals of the bridge are connected to the AC source. So this is connected to the AC source. So this is the basic construction of Wheatstone bridge. So resistance of resistances of two resistors are fixed, and the resistances of one is adjusted until the current passing through the galvanometer decreases to zero. So in order to make this galvanometer to zero condition, these two resistances are anyway fixed. So those have some fixed values. So this resistance is a variable resistance. We can vary this resistance until the current in the galvanometer becomes zero. So when the current in the galvanometer becomes zero, so what happens? Bridge is said to be balanced. So from the balancing condition, we can find out the unknown resistance R4. So R4 is nothing but the unknown resistance, and R1, R2, R3 are nothing but the resistors of known resistance, where R3 is nothing but adjustable. So we can adjust the resistance of R3. So we can say that when no current is flowing in the galvanometer. So when the galvanometer, so I equal to 0. So when no current is flowing through the galvanometer, we can say that the bridge is said to be balanced. So the bridge is said to be balanced condition. So here, so when the bridge is said to be balanced condition, so current so we can say that these two currents are same. So that means you can find out. So current at the node I1 R1 equal to, you can say that I2 R2. So when bridge is said to be balanced, you can say that I1 R1 equal to I2 R2. And next I1 equal to, so here I1 equal to I3 equal to I1. So here the bridge is able to be balanced means this will be, so when it is current is zero, this is open circuit. So whatever the current flowing in this arm is equal to this current, and here also you can say that I1 equal to I3, I2 equal to I4. So you see here, so I1 equal to I3. So you can find out. So I1 equal to I3 equal to total voltage. So what is the total voltage source? E divided by R1 plus R3. And next here I2 equal to I4 equal to E divided by R2 plus R4. So here I2 equal to I4 equal to E divided by R2 plus R4. So, so combining these equations, these above two equations, so you are getting. So anyway, all the currents are same. You can say that E by. So that means here these I1 value substitute in the above equation, and I2 also substitute in above equation. So what you are getting? So E by ER1 by. So you are getting E ER1 divided by R1 plus R2. So that is equal to E. So you are getting R2. So ER2 divided by R1 plus R2. So R2 by R1 plus R2. So anyway, EI is common, no? So that means E get cancelled. So what you are getting? R1 by R1 plus, sorry, R3. So here this is R3, and this is nothing but R2 plus R4. R2 plus R4. So R1 by R1 plus R3 equal to R2 by R2 plus R4. Now cross multiply. So what you are getting? R1 into R2 plus R4 equal to R2 into R1 plus R3. R1 R2 plus R1 R4 equal to R2 R1 plus R2 R3. So here R1 R2 R1, R2 both get cancelled. So what you are getting? R1, R4 equal to R2, R3. So from here, R4 equal to, that is the unknown resistance Rx, equal to R2, R3 by R1. So R2 by R1 into R3. So this is the expression. That means by using this expression, we can find out the unknown resistance. Okay. So this is the about the during balancing condition. So you can find out the unknown resistance. Okay, is it okay? So all of you understood, I think so. The balancing condition. Uh, so so next you need to know about the sensitivity of Wheatstone bridge. So when the pointer of a galvanometer deflects towards right or left hand side, so this means the current is flowing through the galvanometer and bridge is said to be, so that means when when there is current is flowing, when there is some finite amount of current in the galvanometer, so the galvanometer will deflect towards right or left, depends on the current direction. So what happens, bridge is said to be unbalanced condition. So when the current is zero, the bridge is under balanced condition. So when current is not zero, the galvanometer bridge is said to be unbalanced condition. So sensitivity, here sensitivity can be defined as deflection per unit current. So sensitivity is whatever the deflection is there, deflection per unit current. So here amount of deflection is a function of sensitivity of galvanometer. So so the deflection of galvanometer is a function of sensitivity. So so more deflection means you have more sensitivity. That means more indicates that it's more sensitivity to galvanometer. So this is the expression for the sensitivity of Wheatstone bridge. So deflection per current. So S equal to what? D by I. So this is a millimeter. So the galvanometer deflection is in terms of millimeter divided by microamps, or we can call degree by how much degree the galvanometer needle pointer is moving. So degree by microampere, or S equal to radians per microampere. So from this relation S equal to D by I, no? So you can find out the deflection. So you can find out the deflection equal to what? Sensitivity into the current. D equal to S into I. So this is about the sensitivity of a Wheatstone bridge. Now you have to find out means under balancing condition you got the unknown resistance. No? So you have to find out the current in the galvanometer. So that means Ig you uh, uh, need to find out. Okay. So for finding out the current, you need to convert this circuit into Thevenin's equivalent circuit. So Thevenin's equivalent circuit is nothing but it's like I think you are aware of Thevenin's theorem. So Thevenin's theorem is also called as a so short circuit theorem. So that means wherever you want to uh, find out that it's a open circuit theorem, ROC, VTH you have to find out. So let us consider you need to convert this uh, galvanometer to a Thevenin's circuit. So let us consider the galvanometer resistance is RB. So this is an equivalent circuit. So you need to find out the Thevenin's resistance as well as the Thevenin's voltage. So if you see, so RTH, you are getting some RTH. So Ig equal to how much you are getting. So ETH, RTH. So you need to convert this above circuit with the Thevenin's equivalent circuit. So Ia equal to what? So galvanometer current. There is some galvanometer resistance also. So Ia equal to ETH by RTH plus RG. So you should consider this galvanometer as a load resistance. So you have to open circuit that. So Ig equal to what you are getting, ETH by RTH plus RG. So RTH plus RG. So Thevenin's open circuit voltage. So you need to find out Thevenin's open circuit voltage. ECD equal to EAC minus EAD. So ECD equal to, you have to apply KVL across this loop. So what you are getting? So if you apply KVL across this loop, what you are getting, ECD equal to EAD minus EAC, EAC minus EAD. So what is EAC? EAC is nothing but I1 R1, and next EAD is nothing but, one second, 48.
Absent.
Absent.
Numbers calls are compulsory. వాళ్ళకి కాల్ చేయాలి మళ్ళీ లెవెల్కి అప్డేట్ ఇవ్వాలి.
Okay. Okay, we are taking, I'm taking the attendance absentees list, so that's why there is some delay. Okay, so see here, so in it, so so for Thevenin's voltage, you are finding out the KVL across this loop. So what you are getting, ECD equal to EAC minus EAD. So I1 R1 minus I2 R2. So EAC is how much? EAC is I1 R1, EAD is I2 R2. So but I1 equal to what? E by R1 plus R3, E by R1 plus R3, and I2 equal to E by R2 plus R4. I2 equal to E by R2 plus R4. So ECD equal to what? E into R1 by R1 plus R3 minus R2 by R2 plus R4. So as you know, Thevenin's open circuit voltage. So here this is a, so by using we need to find out the Thevenin's resistance. Here R1 is parallel to R3 and R2 is parallel to R4. So that means both resistance are same. RTH you can write as R1 R3 by R1 plus R3, that is equal to R2 R4 by R2 plus R4. So if null detector is now connected between C and D, so you are getting Ig equal to what? So you are getting some galvanometer current. Ig equal to ETH by RTH plus RG, where RTH equal to R1 R3 by R1 plus R3, R is equal to R2 R4 by R2 plus R4, and ETH equal to what? E into R1 by R1 plus R3 minus R2 by R2 plus R4. So this is the Thevenin's voltage and Thevenin's resistance, and from this you will get the galvanometer current. So galvanometer current is ETH by RTH plus RG. So in practice, Wheatstone bridge is used to measure the resistance in the range of several ohms. Okay, so that means R is measured in, is very high. So in order to find out some resistance in terms of mega ohms, we will use this galvanometer. Uh, so sensitivity should be very less. That means galvanometer should be in a balanced condition. Suppose if you want to find some less amount of resistance in terms of ohms or ohms. So you need to use another type of bridge, that is a Kelvin bridge. To determine low values of the resistance, you need to find out the Kelvin bridge. Okay, so this is about the Wheatstone bridge. Coming to the application, it is easy to measure the DC resistance of various wires. So if you want to find the DC resistance, we can use this Wheatstone bridge. You can find out the motor windings, resistance of a motor winding. You can find out the resistance of transformer. You can find out the resistance of coil. So you can use this Wheatstone bridge in telephone companies to locate the cable faults. So these are the applications of Wheatstone bridge. Limitations. So there will be an error. That means when during measurement of low resistance, so low resistance leads contact becomes significant. So introduce some error. So when so here, if you want to find the high resistance measurement, so bridge becomes unbalanced. When the bridge is unbalanced, the galvanometer is insensible. Change in resistance of bridge arm due to heating effects. So means as the resistance will change with the temperature, no. So when there is any heating effect, there will be change in the resistance. If there is change in the resistance, you will not get an exact value during the balancing condition. So here, rise in temperature causes the change in the value of resistance. Excessive current may cause parameter change in the value. So that means the resistance will change with vary with temperature. No? You will not get a proper value of the resistance. So these are the numericals. Yeah. So we'll discuss few numericals based on the Wheatstone bridge. So here is given for the bridge circuit shown, R1 equal to 1000 ohms, R2 equal to 4000 ohms, R3 equal to 100 ohms, R4 equal to 400 ohms. The galvanometer internal resistance is 100 ohms. Current sensitivity, you know, S equal to I by deflection D by I, no. So 100 millimeter by microampere. The battery is 3 volts. Calculate the galvanometer deflection for the imbalance of, so galvanometer is said to be in unbalanced condition. You need to find out the galvanometer deflection at 1 ohm, the resistance R4. The use of calculator, you know, so forbidden means you should not use the calculator. So under balancing condition, R1 by R2 equal to what? R2 by R4. So that means 1000 ohm by 100 ohm equal to 4000 by 1000 ohm. So let there will be an imbalance because of increase in R4 by how much? So here the galvanometer imbalance 1 ohm in the resistance R1. No? So due to increase in 1 ohm in the R4 resistor, the galvanometer is in unbalanced condition. So let us consider R4 equal to what? 400 plus X ohm. So you have to find out the Thevenin's resistance. So Thevenin's resistance is previously you got the Thevenin's resistance, no? So what is Thevenin's resistance? R1 R3 by R1 plus R3, that is equal to R2 R4 by R2 plus R4. So if you see here in this problem, R1 R3. So R1 R3. So what is R1 R3? 1000 into 100 by R1 plus R3. So 1000 into 100 by 1000 plus 100. And next R1 R1 R4, R2 R4, R1 R3, R2 R4 means 4000 into 400 will be increased by X, no? So 4000 into 400 plus X by 440 plus 400 plus 4000 plus 400 is 4400 plus X. So so you'll get RTH as 456 ohms. And next ETH is R3 by R1. So E into R3 by R1 plus R3 plus R4 by R1 plus R4. So if you substitute those values R3 and R1, R1 and R4 values, so 100 by 1000 plus 100 is 1100, 400 plus X by 4400 plus X into what is E3. So 1 by 11 minus 400 you can take common, 1 plus x by 100, 4000 into 1 plus x by 4400. So you are getting 1 by 11, 1 plus x by 400, 1 plus x by 400. So it means this is a like applying binomial expansion and neglecting x2. So if you simplify, so you are getting 3 by 11, 4400 minus 4400 minus 10x by 4400. So you are getting 10x by 4840 into 3. So you are getting ETH as 620 microvolts. X as 1 ohm. So X is nothing but 1 ohm. Now you have to substitute the X as 1 ohm. So what is galvanometer current? ETH Ig equal to, we have seen in the previous slide, ETH by RTH plus RG. So 620 microohms by 456 plus 100. So you are getting 1.114 microamps. You need to find out the deflection. So what is deflection? Sensitivity equal to deflection by current. No? So D equal to S into I. So S into I, this is I, this is I. So galvanometer current, I you got. So galvanometer, what is galvanometer current? This is the galvanometer current, 1.114 microamps into yes. So what is S value? 10 millimeter by microamps. No? 10 millimeter by microamps. So this one cancel. So what you are getting? 11.14 millimeter. So this is the D value. So by using this, you can find out the, he is asked the deflection. No? So calculate the galvanometer deflection. So by using this calculation, so you can by using these relations, we can find out the galvanometer deflection. So this is one problem. I think you understood this problem. And next, the ratio of Wheatstone bridge as shown here: R1 equal to 100 ohms, R2 equal to 100, R1 equal to 1000 ohms, R2 equal to 100 ohms, and R3 equal to 400 ohms, and the unknown resistance Rx equal to 41 ohms. So it is given to 1.45 volts battery with negligible internal resistance. Is connected between R1 and R2. Junctions R3 and R4. So here galvanometer internal resistance is 50 ohms and current sensitivity is 2 millimeter per microamps connected to other corners of bridge. You have to calculate the deflection of the galvanometer caused by the imbalance. You have to find out the D. So as you know, so you have to find out RTH. RTH equal to R1 plus R3 by R1 plus R3 plus R2 into Rx by R2 plus Rx. So substitute those values. RTH you are getting 315 ohms and ETH equal to into E. So here missing into E. R3 by R1 plus R3 minus Rx by Rx plus R3 into E. So if you substitute R3 is 400 divided by 400 plus 1000 minus 41 by 41 plus 100 into 1.5. So if you calculate this value, ETH you are getting 7.6 milliohm. So you have to find out the galvanometer current. Ig equal to what? ETH by RTH plus RG. So that is equal to 7.6 milliohms by 3.5 plus 50. So RG is 50, no? He given in the problem. That is equal to 20.8 milliamps. So galvanometer current is 20.8 milliamps. Now he given deflection. So deflection equal to what? So deflection equal to 2 millimeter per microamps. So this is you know that D equal to what? Formula D equal to S into I. S into I. So that means here 2 millimeter by, so this is S value and this is the galvanometer current Ig. So 2 millimeter per microamps into 20.8. So you are getting 20.8 microamps, no? 20 milliamps. You are getting 41.6 milliamps. So this is how you can find out the deflection when the bridge is said to be in unbalanced deflection of a galvanometer when the bridge is in unbalanced condition. So that means you need to convert the given Wheatstone bridge into Thevenin circuit, and you need to find out the Thevenin's resistance and Thevenin's voltage. So so replace that whole circuit with Thevenin's circuit and replace with the galvanometer resistance, internal resistance. So here the galvanometer internal resistance is negligible, no? So that's why not indicated. So And next you have to find out the galvanometer current, and from this formula, so deflection equal to S into I. So S is already given, so deflection equal to the sensitivity into the galvanometer current. So you can find out like this. Okay.